Okay, good afternoon, everyone. Before I start with a new topic, this is week 7. No? Before I start with a new topic, are there any questions with regards to diodes? Okay, none. Okay, so we're going to start with bipolar junction transistors today, and then the next module would be about field effect transistors, no, metal oxide semiconductor field effect transistors. So I'm going to share what I have for you today. Okay, bipolar junction transistors, or BJTs. So this is what I plan to cover for today and for Thursday. First, we'll discuss the simplified construction and circuit symbols for BJTs. And then the modes of operation. We're going to take up 3 modes of operation: the forward active mode, saturation mode, and cutoff mode. Then we're going to jump into analyzing common emitter transistor circuits. And then we'll dig a little bit deeper on the transistor as an amplifier and on the transistor as a switch. Okay, by the way, this is quite different from the published material that is in UVLE, the material that is published by Dr. Season, Dr. Louis Season. He is the handler in charge of transistors. I think you should use I think you should not forget to refer to the material of Dr. Season. No? He has excellent material which he published, videos of lectures which he personally created. No? It might interest you to know that Dr. Season actually wrote a book on electronic devices and circuits. Okay, first let's discuss simplified construction and circuit symbol. I mentioned to you last time that we weren't going to take up the physics behind semiconductor devices, but I think it's important for me to say a little bit about how both diodes and transistors are constructed. There are 2 types of semiconductors. You have what we call the N-type, and you have the P-type. And the distinction between the two is the charge carriers that are inherent in the semiconductor. So for an N-type, the charge carriers are electrons, which are negative. And in a P-type, the charge carriers are, let me just say, positive. No, I don't want to describe what they are yet at this point. No, so in N-type, the charge carriers are negative, and in a P-type, the charge carriers are positive. Okay, how do you form a diode? A diode is formed by creating a junction between an N-type and a P-type. That's how you form a diode. So very, very simplistically, it looks something like this. You have a semiconductor, you have an N-type, and then you have a P-type. And here you have what we call a junction. Okay. The N-type is your cathode, so that is K, and the P-type is your anode, that is A. In other words, this is equivalent to a diode that is pointing to the left, anode and cathode. That's why you sometimes call your diode a junction diode. Diode, sometimes you refer to your diode as a junction diode. Okay, of course, the material that is used to create this is a semiconductor material. This is a semiconductor material. And the most common semiconductor material currently used in electronic devices is silicon. No? Silicon is the most common. If you take a look at all the electronic devices existing today, I would say 99.9% of all these devices are made from silicon. Okay, I'm not going to explain anymore how a diode works. No? You already know that current is only supported from anode to cathode. No, it is not supported from cathode to anode. Okay, a transistor, a BJT, no? In particular, a BJT, bipolar junction transistor, this contains, sorry about that, this contains two junctions. Okay, you actually have two types of BJTs, two types. Okay. The first is the NPN, and the second is the PNP. You have your NPN transistor and you have your PNP transistor. Again, no, a very simplistic construction. This is putting it very simplistically, but for illustrative purposes, what do this do these constructions look like? No, so for an NPN, okay, essentially you have a P type that is sandwiched between two N types. So this is N, this is P, and this is N. And for a PNP, of course, you can guess already, you have an N type that is sandwiched between two P types. So this is now a P, this is an N, and this is a P. And you attach terminals to each of these. So these are your terminals. One terminal we call the emitter. Okay. Another terminal we call the base, and the third terminal we call the collector. So this is E, this is B, and this is C. So E, let me do it somewhere else. No? E stands for emitter. Okay. B stands for base, and C stands for collector. Emitter, base, collector. Okay, the circuit symbol for an NPN looks like this. This is my collector, this is my base, and this is my emitter. And the circuit symbol for a PNP looks like this. This is my collector, my base, and my emitter. Okay. The arrow, you notice the arrow. This is the direction of current flow when the base to emitter is conducting. When the base to emitter is conducting. Okay, what are the roles of each of the terminals? No? Your emitter this is the source of charge carriers. So you might say the emitter emits charge carriers. The collector, this collects the carriers. And the base, this is used to control current flow or charge flow, no? Well, current flow or charge flow from, okay, between emitter and the collector. Okay, in triple E123, we're going to focus on the NPN transistor. We're going to use the NPN transistor to illustrate BJT concept. So most of the examples and most of the problems that you're going to encounter in this particular course would be using NPN transistors. But you should also be familiar with PNP transistors. You should have familiarity with it, and eventually in 131, then you're going to be using both, because there are circuits that require both NPN and PNP transistors. Okay, so let's consider the NPN transistor. Okay, so I already mentioned that okay, you have a very simplistic construction. This is a simplified construction. So this is NPN. Okay, this is your emitter, your base, your collector. Okay. You actually have two junctions. There are two junctions. This is your emitter base junction. Or sometimes, for simplicity, we just say emitter junction. And this is your collector base junction. You have your emitter base junction and you have your collector base junction. So if you think about it, okay, remember I said that a diode is formed when you have a NP or PN junction. So if you think about it, this actually, at first glance, will seem to you like two diodes that are in series. So parang ganito siya, no? I have a diode this way, then I have another diode this way, and then this is my base. Okay, so this is at first glance, no? Yeah, this is a first glance. So if you think about this as what we call two back-to-back diodes, under normal circumstances, current cannot flow from emitter to collector. So I'll just mention that, no? Under normal circumstances, current cannot flow from E to C. Okay. But why did we say here? Why did we say here that there are going to be charge carriers that will flow from the emitter and that will be collected by the collector? Well, in reality, this region is very, very thin. No? So in reality, the base is very thin. No? So that when you have charges flowing, for example, in this case, no, it's going to be electrons because this is an N-type. Remember what I said, an N-type has electrons or negative charge carriers. So electrons are going to come from the emitter. No? If the voltages applied are correct, electrons are going to flow into the emitter. Because this is very, very thin, not all of the electrons will go back to the base. Instead, some of the electrons will cross over to the collector and be collected by the collector. No? So in reality, the base is very thin, okay, that the electrons coming from the emitter cross into the collector. Okay. And it is the current at the base that will actually control the current flow between the emitter and the collector. So that's how a transistor intuitively, or in a gist works. No, so I'm not going to go beyond that. The physics behind the transistor again is going to be discussed in EEE 131. So in this particular course, we're really going to only discuss how it behaves, no, in a circuit. So we're going to discuss its model. So you have the different modes of operation of a transistor. So I'll go back. No? So this is my NPN transistor. This is my collector. This is my base. This is my emitter. I have two junctions. Okay. I have my emitter base junction. And I also have my collector base junction. Okay. I have 4 possible combinations. For my emitter base junction, that can be, okay, let me write it this way. No? Your emitter base junction can be forward biased or can be reverse biased. Same thing with your collector base junction. Your collector base junction can be forward biased or can be reverse biased. So remember, this is an NPN. No? This is an NPN. So if the base emitter is forward biased, your current is from base to emitter. Okay. If the base collector is forward biased, your current is from base to collector. If it were a PNP, the direction would be the opposite. Because as I mentioned here, the diode, okay, the P is the anode side and the N is the cathode side of a junction diode or a PN diode. So there are 4 possibilities, 4 possible combinations. Okay. Let me fill up what the operating modes are going to be, or the modes of operation. When the collector base is reverse biased and the emitter base is forward biased, you call this the forward active mode. This is called the forward active mode. When both are forward biased, both the emitter junction and the collector junction, you call this saturated mode. Okay. When the collector base is reverse biased and the emitter base is forward biased, this is called your reverse active mode. And finally, when both emitter and collector junctions are reverse biased, this is called cutoff mode. So those are your 4 modes of operation. Now, of those 4 modes of operation, usually only 3 are employed. So itong tatlo, these are the modes that are usually used. The reverse active mode is in reality not used. This is not used. Usually, what happens is a transistor gets into reverse active mode when you make a mistake in its connection. Otherwise, you never use a transistor in reverse active mode. Okay. By the way, no, for your NPN transistor, the reference directions for current will be as follows. Okay, this is going to be your collector current. It is going to be inward. This is going to be your base current. Okay, it is also going to be inward. Now, you can apply KCL to the transistor because a transistor cannot accumulate any charge. And it follows that you will get an emitter current that is outward, where your emitter current should be equal to your base current plus your collector current. So this satisfies Kirchhoff's current law. Okay, any questions so far? Any questions so far? Everything okay so far? Okay, give me some feedback. No, I want to make sure I'm not losing you. Okay, good. Okay, so let's discuss the different modes of operation in more detail. No, forward active mode. Sometimes we just say active mode, no, because usually we don't use the transistor in reverse active mode. So pag sinabing active mode, then the implication is forward active mode. So what is active mode? So I said that the emitter base is forward biased, and then the collector base is reverse biased. Okay, the characteristic of a transistor when it is in active mode is it acts like a controlled current source. So in active mode, it is actually a current controlled current source. Okay. The model for your transistor is as follows. No? If this is my transistor, so what is its behavioral model? Okay, so this is again IC, IB, IE. The behavioral model of your transistor is like this. By the way, this is your base, this is your collector, this is your emitter. So this is my base. What I have here is a diode. Okay. Okay. This is now my emitter. And then between my emitter and collector, I have a controlled current source this way, where my controlled current source is equal to beta times IB, where this is IB. So that is the model. That is the model of my transistor, my bipolar junction transistor in active mode. So if you take a look at the simplified construction, Okay, remember these are simplified construction. Okay, from base to emitter, it's really just a diode, no? You really just see a diode, no? Because that's from P to N. So it's rightfully modeled in the model that I just constructed. Now, from the collector to emitter, it is a controlled current source. Remember what I said, you have electrons coming from here. No, actually, base to emitter means positive charge carriers from P to N, no? Because current is always positive charge carriers. But in reality, no, because this is an NPN, it's really electrons flowing from left to right. So electrons will be flowing to the right. Now, instead of recombining with holes and coming out in the base, because this is very thin, some of these electrons are going to go here to the collector. And since the collector junction is reverse biased, so I mentioned that in active mode, your collector junction is reverse biased. That means the collector is more positive with respect to the base. And we're talking about electrons. So what's going to happen is the electrons, no, from here are going to cross the base, and it's going to see a positive voltage here. So it's going to accelerate toward the collector. That's why you call it the collector, no? Collector, tagasalo. Sinasalo niya yung mga electrons na galing sa emitter. And that's why if you have electrons flowing to the right, that is current now flowing to the left, no? Because current is defined as flow of positive charges. So that's what we're describing in this model. So this is the base emitter diode. Okay. And then the electrons flowing this way constitutes a current flowing the other direction, where the value of that current is a constant beta multiplied by IB. So beta, this is a parameter of the transistor. Okay, it's a parameter of the transistor. It's called the common emitter large signal current gain. I don't want you to get intimidated by that. Let's just say it's what the base current is multiplied with to get the collector current. No? And the typical values for beta typically would be somewhere between 50 and 200. No? In the examples that we're going to use in this course, usually we say beta is equal to 100. No? That's a very, very typical value. Beta is equal to 100. Okay. So if you take a look at the relationship between IC, okay, this is your collector current, and your base current, it's really just going to be a straight line. Okay, where the slope of that straight line is going to be beta. Okay. Now, what is the application of your transistor in the active mode? Usually, the application is amplifier circuits. So again, this is just the model. So this is the same thing as I drew here. It's exactly the same thing. This is my model. I just wanted to show it here with an input port and an output port, no? But otherwise, it's really the same thing. Okay. So IC is equal to beta times IB, and this is a typical application. This is a simple transistor amplifier. What is an amplifier? An amplifier is a device that amplifies the power output of a weak signal, no? Or rather, let me repeat that. No, it's a device that amplifies a weak signal into a stronger signal. No, stronger signal in the sense that it can deliver more power than the original signal. But there's a catch. No? In an amplifier, the information at the input must be preserved at the output. So amplifier So yeah, the info at the input must be preserved at the output. Okay, in this particular case, if I have an input this way, okay, this amplifier is going to make the amplitude of my signal larger. So the amplitude becomes larger, but the information that was here is preserved here. Now you're going to find out in a while that this amplifier actually has a negative gain. In other words, as my input is increasing, my output will be decreasing. But that's okay, because whatever information is here can still be retrieved from the output. So that is your amplifier. Okay, what is the next mode that I want to talk about? Next mode that I want to talk about is saturation. So if I go back to here, saturation is when both the collector base and the emitter base are forward biased. So emitter base and collector base are both forward biased. Okay, in order to illustrate what saturation is, I'm going to show you a typical circuit. So this is VCC, that's my power supply voltage. RC would be my what we call the collector resistance that is connected to your collector. This is your collector. Emitter, I connect this to ground. Okay. And then let me connect a variable input voltage to my base through a resistor R sub B. So let me call this B sub B. Okay, and I'm going to get my output here at my collector. So this is my output, V sub O, which is equal to VCE. Okay. Okay, if you take a look, now, remember what I said, between the base and the emitter, what it sees is just a diode. Between the base and the emitter, what it sees is just a diode. So it's pretty much the same as your model for here, the base and the emitter. Okay, so I can actually apply KVL here. I can actually apply KVL to this particular loop. What is KVL? Applied to your base emitter circuit. Okay, I'm going to get V sub B minus, okay, this is now IB, RB, okay, minus, this is VBE, minus VBE is equal to 0. IB, I can now compute for IB. This is going to be VB minus VBE all over RB. So as I increase VB, I will increase I sub B. By the way, if this is a silicon transistor, if silicon transistor, just like the diode VBE, we say, is approximately equal to 0.7 volts. That is the forward voltage of a conducting diode. Anyway, the point I want to make is, as we increase V sub B, let's say VBE being almost constant, IB will just increase. If IB increases, what is now IC? IC, assuming this is in active mode, that's equal to beta IB. This is assuming active mode. Now we're talking about saturation mode, no? But let's first assume that it is in active mode. Okay. And if I get the output voltage V sub O, this is applying incremental KVL. V sub O is just VCC minus the voltage across my collector resistor. So V sub O is just VCC minus the voltage across my collector resistor. This is equal to IC times RC. Okay, which is VCC minus, we said IC is equal to beta IB. So beta VB minus VBE over RB. So this is now IB, no? IB here, times RC. Okay. If I plot V sub O versus VB, okay, V sub O versus VB. Okay, when VB is equal to 0, obviously this is not forward biased. Obviously this is not forward biased. What does it take for a diode to start conducting? Can I hear? What will it take for this diode to start conducting? How many volts should the open circuit voltage across it be? I'm just trying to wake you guys up. Anyone? Okay. For this diode to start conducting, if I get the open circuit voltage across it, the open circuit voltage has to be greater than or equal to 0.7. So when V sub B is equal to 0, okay, in essence, my I sub B will be equal to 0, and my output will be VCC, no? Because this is going to be 0. This is going to be 0. My output will be VCC. Okay. When will IB become not 0? No? So this is going to stay VCC until V sub B now gets to about 0.7. Because when V sub B is equal to 0.7, okay, or when V sub B exceeds 0.7, now I'm going to get a current flowing here. I'm going to get a current flowing here. And that current is going to be multiplied by beta, okay? And then my V sub O will be VCC minus IC now, that's beta IB times RC. So this is going to start to decrease. And the decrease is going to be linear. Okay. Now, will it decrease forever? Will it decrease forever? The answer is no. At some point, when it reaches a value which we will call VCE SAT, okay, at some point, even if I increase V sub B further, kahit nalakihan ko pa tong V sub B, kahit nalakihan ko pa yung value ng IB, no? Because as I increase V sub B, the value of IB is going to increase. This is not going to become any smaller. That is going to stay now constant. And this is now what we say is saturated. This is now what we say the transistor is saturated. In other words, your output voltage cannot become negative. No? This will not, if we increase V sub B so that I sub B increases, this will not continue to go down. At some point, the voltage, the output voltage will stay at VCE sat. And for silicon, VCE sat is approximately equal to 0.2 volts. Okay. Now, when does this happen? As V sub O is decreasing, that is, as VCE is decreasing, so habang lumiliit yung value of voltage between current, collector, and emitter, okay, this one is becoming less and less reverse biased. No? This is becoming less and less reverse biased. When VCE is large, so here it's large, so this is positive with respect to the base. No? But remember, this is P and this is N, so ito reverse bias to. This is reverse biased. No? But as VCE gets smaller and smaller, okay, this terminal becomes less positive with respect to the base. And it comes to a point where now this diode becomes forward biased. And when does that happen? That happens when the collector to emitter voltage now becomes approximately equal to, for silicon, 0.2 volts. And further increasing I sub B by increasing VB will not cause your output to go down any further. And that's what we call saturation. That's what we call saturation. So when does this happen? When does this happen? Okay, this happens when V sub O is equal to VCE sat. So you can compute, no? When this is VCE sat, no? Pag itong expression ng V sub O is equal to VCE sat, no? So VCE sat is equal to VCC minus beta VB minus VBE over RB times RC. You can compute the value of VB in which this will happen. Or you can compute the value of IB in which this will happen. Are there any questions? Are there any questions? Okay, so just to recap, saturation mode, both the emitter base and the collector base junctions are forward biased. The collector to emitter voltage is very small. It's about 0.2 volts for silicon. Increasing I sub B will not increase I sub C. So in my previous example, I increased I sub B by increasing VB. Increasing I sub B will not increase I sub C. No? In other words, I sub C will stay constant at IC sat, which is now defined by my external circuit. And actually, when you think about the transistor, it looks like a closed switch. If you think about your collector resistor as your load, think about RC as your load. If the voltage across your transistor is very small, for silicon, for example, if that's 0.2 volts, 0.2 volts compared to, let's say, a large VCC, then it's almost as if the entire VCC is applied across my load. Ulit, ano? Pag maliit na maliit yung voltage between my collector and emitter, and for silicon, the smallest that can be is about 0.2 volts, then it looks like my entire VCC is going to be applied across my load. And therefore, this actually switched my load on. In effect, it switched my load on. No? So this particular arrangement, when you are in saturation mode, looks like a closed switch. So that is saturation mode. Now, the third mode is cutoff mode. And these are when both the emitter base and the collector base junctions are reverse biased. So if I again take a look at my simplistic construction, so this is N, P, N. How do I reverse bias my, so this is my emitter, my base, my collector. How do I reverse bias my emitter base? I apply a voltage here where this is positive, where your N side is positive with respect to your P side. And then how do I reverse bias this? Okay, I reverse bias this by by having my collector N positive with respect to my P. Okay, so these are both reverse biased. This is VEB, okay, and this is VCB. These are both reverse biased. So if this is reverse biased, I cannot have any current flowing between my base and my emitter. No? If this is reverse biased, I also cannot have any current flowing between my base and my collector. So my base current will be 0, my collector current will be 0, and therefore my emitter current will also be equal to 0, no? Because IE is equal to IB plus IC. So everything will be 0. There's no current that will flow anywhere in the transistor. And what will it look like now? It will now look like an open switch. So again, if you think about your collector resistor as your load, no, when this is cut off, there's no current flowing from my collector to my emitter. So that's like an open circuit or an open switch. Okay, I just wanted to show this graph to you. This is the relationship between IB and IC when my power supply voltage is assumed constant or unchanging. So when IB is equal to 0 and IC is equal to 0, we're at this point where your transistor is cut off. If my collector base is reverse biased and I start to get base current to flow, then that means my emitter base will be forward biased. Then I'm going to get IC is equal to beta IB. No? So this is now in the active region. IC is equal to beta IB. But at some point, further increasing my IB, will no longer increase my IC. At some point, this is going to start becoming constant at IC sat. And IC sat is dictated by my external circuit. So I have to be able to compute for IC sat on a case-to-case basis. That would depend on the resistors that are connected to my circuit and also on the power supply voltage. Any questions so far? Any questions before I proceed? If you need time to digest anything, please ask your questions now, no? because baka naman masyadong mabilis para sa inyo, no? Okay. Okay, we have different transistor configurations. The most widely used transistor configuration is what we call the common emitter configuration. This is the most widely used transistor configuration. In the common emitter configuration, the emitter is normally assigned as reference node. So in this particular case, the emitter is grounded. Now, the emitter does not have to be directly grounded to be assigned as a reference. Sometimes there is a resistor between the emitter and the ground, no? But it is still called the common emitter configuration. But in this particular example, the emitter is directly grounded. And so I have my input voltage here with respect to my emitter, and my output also with respect to my emitter. That's why you call it common emitter. There are other configurations, the common collector, the common base. In EEE 123, since this is really introductory, we are not going to take up the other configurations in too much detail. No, we might mention it, but it's not going to be taken up in too much detail. No? And what are the steps in analyzing common emitter circuits? So I tried to break it down into a few rules. No? Okay, what's the first step? The first step, like what we did when I started to explain saturation, you apply KVL to the base emitter loop to determine I sub B. Apply KVL to the base emitter loop to determine I sub B. Now, one of the things you have to determine, no, when you analyze the base emitter loop is if indeed current will flow or not flow. And for you to determine whether current will flow, you have to determine whether the base emitter diode is conducting. And you already know at this point how to determine whether a diode is conducting or not. That was one of the subject matter of module 6. So dapat alam ninyo no, paano malaman kung nagko-conduct yung diode o hindi. Now for silicon transistors, the base emitter diode is like an ordinary silicon diode in the voltage that is across it while it is conducting, which is approximately 0.7 volts. Again, first step, determine I sub B. Now, if we find in analyzing the base emitter circuit that there is no current that will flow, then automatically we say it is cut off. If no current will flow in the base, then automatically we say it is cut off. If it is cut off, then there is no voltage drop across any resistance connected to your collector. There is going to be no voltage drop across any resistance connected to your collector. So, for example, no, I have a resistor here, RC. So this is VCC. This is V sub O. Okay, and I already determined that I sub B is equal to 0. If I sub B is equal to 0, I sub C, no, this one will also be equal to 0. If I sub C is equal to 0, that means there is no voltage drop across this, and therefore V sub O is just VCC. Whatever voltage here will also be the voltage here, no, because the voltage drop across your R sub C will be equal to 0. And okay, your transistor is in cutoff mode, and that's it. You don't have to analyze the circuit further. Sorry. You don't have to analyze the circuit further. You already know that I sub B is 0, I sub C is 0, and your V out will be equal to VCC. Now, what if I sub B that you computed here is not equal to 0? What you will do is you first make the assumption that the transistor is in active mode, such that IC is equal to beta times I sub B. Again, no? We compute the base current here. If it is not equal to 0, then we assume that your transistor is in active mode, such that IC is equal to beta times I sub B. Then we can solve for VCE by applying KVL to the collector emitter loop. Now, if VCE is greater than VCE SAT, then the assumption that the transistor is in active mode is valid. If we discover after computing for VCE na mas malaki siya sa VCE SAT, then tama yung assumption natin dito sa step na to, no? It is in active mode. And whatever value of I sub C we computed here is correct. Now, I already mentioned VCE SAT for silicon transistors is typically 0.2 volts. Otherwise, if we see that VCE is less than VCE SAT, then itong active mode assumption will be invalid. In fact, if VCE is less than VCE SAT, that means that the transistor already got to the point where your collector-base junction is forward biased. Hindi na siya reverse biased. So that is the condition for active mode operation, that it has to be reverse biased. But if VCE already became so small, no, that it is already less than VCE SAT, or equal to VCE SAT rather, then that means your collector base is already forward biased. And that means your transistor is already saturated. Your transistor is already saturated. And therefore, VCE is just VCE SAT. Whatever you computed for VCE in this particular step, in the fourth step, is not valid. No? I just know that VCE will be VCE SAT. So if I know what VCE is at, I can recalculate the value of IC. Okay. Let's do an exercise. Let's do an exercise. So this is my transistor circuit. I have an input voltage. Input voltage applied through a resistor to the base of my NPN transistor. I get my output at the collector. So my output is actually equal to VCE. Vout is equal to VCE. I have a collector resistor between my supply voltage and my collector. And these are the values of my circuit elements and also of my transistor parameters. No, what are my transistor parameters? My transistor parameters, and you can pick this up. No, if you have a transistor, you can pick this up in the data sheet of your transistor. That is VCE SAT. Here I said VBE active, no, VBE active, but actually that's just VBE really. And then beta. And then here I have VCC, RC, and RB. Okay, fill up the table below. Okay, when Vin is equal to 0, can someone give me an answer? What will be the value of Vout? When Vin is equal to 0, what will be the value of Vout?
5 volts po.
Yeah, bakit 5 volts, Albert?
Kasi po magiging 0 po yung IB, then also IC po is 0. Wala pong voltage drop sa RC. So VCC is equals, Vout is equals to VCC.
Yeah, that's right. No? So tama, no? So this is going to be equal to 5 volts. Albert, what about when Vin is equal to 0.7? Ano yung Vout?
I think 5 volts din po.
Because 0 pa rin yung current.
0 pa rin po yung IB.
Okay, that's right. No? Okay, now let's go to the case where Vin is equal to 0.8. Vin is equal to 0.8. So yung dito sa step na to, I said, okay, first thing that you do is you apply KVL to the base emitter loop to determine I sub B. No? So let's try to determine for V in equal to 0.8 what ICE of B is. Ano? So for V in equal to 0.8 volts, let us determine ICE of B. No? Okay, so we will apply KVL to the base emitter loop. No? So ano yung KVL dito? V in minus IBRB minus VBE is equal to 0. No? So V in minus IBRB minus VBE is equal to 0. Now this is silicon, so VBE is 0.7. Okay, so I can now compute for IB. IB is equal to V in minus 0.7 all over RB. But V in is equal to 0.8. No? So if I do this, okay, if I do this, what will be, sorry, I don't, yeah, what will be my IB? No? So this is 0.8 minus 0.7 over 10K, no? Because RB is equal to 10K. I'm going to get ISO B is equal to 0.01 MA, or if we use engineering notation, this is 10 microamperes. Okay. ISO C is going to be equal to beta IB. Beta is equal to 100. So what is this going to be? This is going to be now 1 MA. No? This is going to be 100 times 0.01 MA or 1 MA. Okay, what's my next step? No? So nakuha ko na yung ISO C, I'm assuming that it is active mode. No? So nakuha ko na yung ISO C, beta IB. So the next step is solve for VCE by applying KVL to the collector emitter loop. No? So ano yung collector emitter loop? Ito yon, ano? Ito yung collector emitter loop, no? This loop. So VCE or V out is VCC minus IC RC. No? V out is VCC minus IC RC. VCC is 5 volts, IC is 1 MA, RC is 1K. What is 1 MA times 1K? This is just 1 volt. No, this is 1 volt. So V out is just 4 volts. Okay. Tapos na ba tayo? No? Check. No? Don't forget that step. No? After you compute for VCE, check if VCE is greater than VCE SAT. You always perform this check. Is VCE greater than VCE SAT? In this case, 4 volts, since 4 volts is greater than VCE SAT, then the assumption that it is in active mode when V in is equal to 0.8 volts is correct. Remember, no, we're computing for the conditions of the transistor when V in is equal to 0.8 volts. No, we computed for VCE that's greater than VCE SAT. Therefore, our assumption that it is in active mode is correct. No, remember, we can only use this equation if it is in active mode. IC is equal to beta times IB. So tama, no? So this is 4 volts. Okay, this is 4 volts. Okay. You can continue to do this, no? just do it as an exercise. I'm going to post this this material in no no in Uvle, so you can just fill in these values. Now I want to go to the case where V in is equal to 1.2 volts dito. Let's take a look at this, no? So what if V in is equal to 1.2 volts? Okay, so I'll compute first for IB. Since step 1 is always compute for IB. IB is V in minus 0.7 over RB. Okay, so 1.2 minus 0.7 is 5. 5 divided by 10K. This is going to be 0.05 MA. 5 divided by 10K is 0.05 MA. Okay, 0.05 MA. Okay, what is, so again, the next step, no, we assume active mode. So IC is equal to beta times IB. So that's equal to 100 times 0.05 MA. I'm going to get 5 MA. And then I compute for V out, which is VCE. No? V out, which is equal to VCE. That is now VCC minus ICRC. No? So what is this? VCC is 5 minus 5 MA times 1K. No? But 5 MA times 1K is also 5 volts. So this is going to be equal to 0. Okay, I have to compare now VCE to VCE SAT. I have to compare VCE to VCE SAT. Since VCE, which is 0, is less than VCE SAT, okay, assumption that it is in active mode is wrong. Mali yung assumption na active mode, no? So again, let's go back here, no? We discovered that VCE is less than VCE SAT. Therefore, the assumption that it is in active mode is wrong. In that case, ano yung VCE natin? So what should VCE be? Or what should V out be? Anyone? Ryan, what should V out be?
Oh, pardon, sir?
So,
V out?
Yeah, what will V out be, or VCE? So we computed it to be equal to 0. Now we saw that VCE is less than VCE SAT. So the assumption that it is in active mode is wrong. So what is the actual value of V out? Are you stumped? How about Albert? Anong value ng V out? Okay.
Is it equal to 0? Or
no, that's that's what I was saying, no? Here I computed it and it's equal to 0, no? I computed it, no? But remember that after computing for VCE, no? So here I computed it, no? This step, it's equal to 0. After computing for VCE, I have to compare that to VCE SAT. And I saw that it is not greater than VCE SAT. It is actually less than VCE SAT. And therefore, this assumption is wrong. No? My IC is not equal to beta times IB. Now, what will be the value of VCE SAT? Okay, it's right here, no? It's right here. VCE, sorry, what will be the value of VCE? VCE will just be equal now to VCE SAT. Okay. So what will
Oh,
happen?
so it's like the cutoff thing, sir. Like
Yeah, that's right. No?
the graph.
So this
Oh.
is now VCE is now going to be VCE SAT, which is now going to be 0.2 volts. No? If you recall, here, no? If you recall this, we reached a point. We reached a point that we thought we're already here, no? But actually, it would not have gone beyond this, no? Because yeah, VCE will continue to go down, but when it reaches VCE SAT, it will stay now at VCE SAT. No? So that's what happened here. So let me go back. Let me go back. So VCE will be now here 0.2. Sorry about that. This is now going to be 0.2 volts. And if I wanted to compute for IC, no? Okay, I can use this equation. Okay, VCE is equal to VCC minus ICRC. Okay, this is 0.2 is 5 minus IC times 1K. And therefore I can compute now for IC. No? My IC would be equal to 5 minus 0.2 over 1K. No? I don't have that value. Let me compute for it. No? A 4.8 MA. That would be 4.8 MA. As a matter of fact, no, that's why I inserted this. This is the exact input voltage when VCE becomes equal to VCE SAT. So here, this is 0.2 volts. So I'm going to stop here. No, like I said, try to fill this up on your own. Okay, try to fill this up on your own. I'll just insert here the answers. So this is 2.6 volts. This is 1.0 volts, and this is 0.5 volts. And just try to solve this on your own. And we'll stop first there. No? So in the next meeting, I'm going to describe in more detail how a transistor can act as an amplifier. Are there any questions? Any questions? Okay, so if there are no questions, try to absorb what I presented here. Again, no, I recommend that you take a look at the material that was posted by Dr. Season. Like I said, I find it to be very good material that he posted, and this is really just to supplement that. Okay, so that's all for today. No, so if you don't have any, well, I'll stick around on just in case you have any more questions. Okay, thank you.
Thank you po.
Thank you, sir.
Okay.